That was two.
It's supposed to grow.
And those who are lactose intolerant can't,
Oh, yeah, just,
right? Like cast and tartar, you can't go to green cheese, right?
okay.
Is this good? All right, are we rolling? All right. Ladies and gentlemen, tonight we will hear from Kevin McLaughlin about visiting the Large Interferometer Gravity Observatory. He has been a member of the Warren Astronomical Society since 2017. He worked in both the aerospace and automotive sectors and has multiple patents and publications across a wide range of technical areas, including automotive safety, motor control, vehicle steering control, and, most exciting for us, satellite control and operations. I hope you saw his wonderful presentation on launching a satellite, so that's still up on YouTube if you want to see it. And he is presently studying physics at Wayne State University. Ladies and gentlemen, Kevin McLaughlin.
Sorry. Which is the next button?
The top one.
Very good. Thanks. So, how I got interested in this, there's a professor from Villanova, her name's Amber Stuber, and she gave a talk at Wayne State, one of the colloquia on gravity waves last April. And then I just happened to be in New Orleans with my wife. We were down in that area, New Orleans, Baton Rouge. We were actually there for a jazz festival. And so we decided to try to tour the facility. And at the end of the talk, I'll talk about how to do it if you ever are in that area and you want to get a tour. But first, just to set everything up, I just want to talk about gravity waves, just so we all know what this is all about. So we'll talk a little about what is LIGO. You know, typical observatories that we talk about all the time, they point in a direction. And they collect electromagnetic radiation, everything from radio waves all the way to gamma rays, visible light. We all know this is just in the middle, and it goes from kind of lowest energy to highest energy over there with gamma rays. And electromagnetic radiation, those are all just photons. They're emitted when electrons change levels, or when atomic nuclei change levels. You get gamma rays and that type of thing out of that. And so the gamma rays, X-rays, and everything are all examples of the electromagnetic radiation. And the key thing here is that the gravity waves, they're not electromagnetic. It's totally different. And that's kind of the interesting part about what this whole observatory is. So gravity waves occur when any mass accelerates. So I guess if I'm doing this, I'm kind of creating gravity waves, to be honest. But they're so small, it's ridiculous. They were predicted by Einstein back in 1916 with his general relativity paper. And what happens is space actually gets squeezed and stretched. So these two masses here, they're at a certain length, and if a gravity wave comes through, the length actually changes and goes back and forth. So it's nothing to do with electromagnetic radiation. It's a totally different thing. And the idea is to try to measure that delta length change as a function of time. And just some general properties of gravity waves. They propagate at the speed of light. So just like anything, just like the light you see from the sun or any place else, they go right at the speed of light. They travel unimpeded through the universe. So they interact really weakly with matter. So if a gravity wave comes and it just goes right through the Earth, right through the sun, right through pretty much everything. So they don't get impeded by dust and all this kind of stuff that we have problems with electromagnetic radiation. They contain information, not images. This is kind of an important thing. So they're more similar to like water waves. So if you're sitting at a beach and it's all calm and then all of a sudden you see some waves come up, you know that was probably a boat went by or something like that. They're indicative of an event, but they're not, you can't image with them. As an example, a 500 hertz gravity wave has a length of about 600 kilometers. So they're these huge wave-like things. And they're kind of the same order of the objects that create them. So you can't image with them. You know, if you want to image with something, your wavelength has to be much smaller than what you're trying to image with. This is a minor thing. There's two polarizations. You know, electromagnetic waves are kind of cool if you have sunglasses and they're polarized. If you take one and then you take another and you put it this way, you can't see through them. gravity waves, they're not, so that means they're polarized, that there's a horizontal and vertical. Gravity waves are actually polarized at 45 degrees, which is kind of a weird little thing. Take an electromagnetic wave, if I rotate it around in a circle, it looks exactly the same. A gravity wave, it's 180 degrees. So, so that might, when you see these antennas, they'll look a little different than a typical antenna. So, and a gravity wave detector is like an antenna. It senses frequency, how fast it's going, its amplitude, how much it's moving back and forth, and then the direction of the wave where it came in space. In fact, it's called an observatory now, but the first paper it was written by this guy named Rainer Weiss, who was one of the Nobel Prize winners, and the original paper with the design was called Electromagnetically Coupled Broadband Gravitational Antenna. So he called it an antenna back then when he first came up with the idea, but it's they really don't call it antenna. It's not ubiquitous anyways in the literature. So it's called the Large Interferometer Gravity Wave Observatory. So let's talk just a little about what an interferometer is. Interferometer was invented by McLaughlin in the late 1880s, and he was actually at the U.S. Naval Academy at that time. And you can think of it as kind of like this: it's an interferometer. So and what it does is light interference is used to measure the speed of light in different directions. So at that time, there was this, nobody knew that the speed of light was constant everywhere, and they were trying to show that it was actually not constant. So the idea was if the Earth's moving that way, if I can measure the speed of light in this direction, it'll be different. And I'll see a different little interference pattern when I do that. So here's an example of the interferometer. So can't really, the light, get the laser to work here.
The very top one.
There it is. Okay, great. So the input comes in here, and then it goes through a beam splitter. And some of it goes down this path, some of it goes down this path, and then it comes back out, and you get these little, you get a pattern over here. And the output, it's either constructive or it's destructive. So if the waves are exactly the same here, if they're exactly the same, then when I add them together, I get double the waves. If they're shifted just a little, and they might be shifted just a little because this path is just a little longer than this path, so this thing gets shifted, I don't get anything out. So I get dark and light spots and everything like that. Well, what they found when they used the interferometer and they moved it around in different directions, it was always the same. And this was kind of the goods that light was a famous null result because they didn't see anything. Because speed of light was measured the same in both directions. So this is the technology that gets used. And LIGO's interferometer measures changes in length due to the gravity waves. So again, the gravity waves, what it does is it stretches in one direction and it pulls in the other direction. And length changes are measured with this interferometer. So this is actually what the LIGO looks like here. There's two legs. This is kind of reversed, if you can imagine this. I couldn't get a picture with it pointed this way. So this leg is this one over here, and this leg is this. These are 2.5 miles long, 2.5 miles back and forth, and it's in a tube that's about 1.5 meters high. So length changes are measured with this interferometer, and the length changes can be measured to 1/10,000th the diameter of a proton. It's kind of almost, it's incomprehensible actually for me. And the gravity, as I said, the gravitational waves, they travel at the speed of light. And the frequency range that this can measure in is in about 30 hertz to 7 kilohertz. So that's the same range as our ears. I mean, if we're little kids, we can hear up to 20, but maybe we can hear up to 12 or a little older, or 15. And the wavelength is from about 10,000 kilometers to about 42 kilometers. If you take these two numbers and these two numbers and you multiply them by, you get the speed of light. I just rounded them. It's about the speed of light. So this is what the interferometer looks like here, and I'm going to talk about some of the technology that's used in this whole thing. So both 4-kilometer long tubes are at a near vacuum. It's one of the best vacuums on the planet. The LIGO people, Amber Stuber, she was like, it's better than the Large Hadron Collider, but their literature on their site says the Large Hadron Collider is a little not. It's about 10,000 cubic meters of space. And, I was going to measure this room before I got in here. This room's kind of that order, to be honest, about 10,000 cubic meters, might be maybe 2 of these rooms, something like that. But if you take all the air out, the air that is left when you get it down to the vacuum fits in a shot glass. So you get rid of all the air and you just got one little shot glass of air that you dump back in, and that's what the vacuum is at. So there's hardly any particles in these tubes. What happens is, and the light reflects back and forth using what's called a Fabry-Perot cavity. So what they did is they added some mirrors. So here, the light just came in and went back. They have these 2 mirrors right here and right here. What that does, it's like an amplifier, and the light goes back and forth and back and forth. And it goes back and forth about 280 times in this thing. So it gives an effective length of about 1,100 kilometers. And so that means the light arms are, believe it or not, about 150,000 times longer than Michelson's original one. So they took this little device and said, let's just make this incredibly huge thing. It's really amazing. The mirrors are suspended like pendulums. In fact, the first one, if you look at it, there was a LIGO, and they call this LIGO A, but they've kind of dropped the A, and they just call it LIGO now. The original one was just a mirror that was on 2 wires. They're real special materials, and they just hung there. Because what you're trying to measure is the distance from here to here, and the distance from here to here to see if it's changing as the gravity wave comes through. So the mirror, it can move up and down. You have to control it. It can move back and forth. You have to control it. You have to control all its rotation. All you want it to be is free. It's just free in this one direction, so it can move back and forth. So again, the first one was a simple hanging mirror. It was updated around 2010. And the mirrors they call it a free-falling mass. You'll see that term if you read anything about these. And there's all these passive and active methods to control it. And this is what the new mirror looks like. It's got all these crazy proof masses. Oops, let me just go back. It's got all these proof masses on here and different. These are like glass. They call it's like a silica fiber. It's like a glass fiber that holds all the mirrors so that they don't move much with temperature. And there's one of these type of mechanisms here, 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 here. It's a really complicated control system to keep the whole thing so it doesn't move, so it just can move back and forth like this.
How much mass, do you know?
Those are 40 kilograms. The mirror is actually.
Thank you.
And when you see the mirror, this is the weirdest thing, okay? Because you look the mirror, you can just look right through. It's kind of odd, because you always think of a mirror, you got it, because it's a different wavelength of light that it's using in this laser. So it's transparent to visible light, but not to the, and I don't remember the wavelength that they use in this, so I don't have any information on the laser in this. So they have shock absorbers and voice coil actuators. Voice coil actuators are speakers, actually. So you can just kind of move this thing back and forth, just like a speaker. It's all connected, so there's no friction. They use these fused silica wires, which are like glass. Yeah, so each mirror is about 40 kilograms. And so in order to do this, you need 2 LIGOs. This is the key to everything. So there's one that's in Livingston, Louisiana, and that's the one we went to. They call it LLO. And then there's a LIGO in Hanford, Washington, or they call it LHO. And anybody know Hanford, Washington? What it's famous for?
Yeah, I've been there.
Yeah?
Yep.
It's where they built, it's where they did the plutonium for the first atomic bomb. And so it's a kind of a polluted site, so I guess it was available with a lot of they wanted a space really far away. So, and when I heard Dr. Stuber talking about the one in Louisiana, she talked about it like it was really out in the middle of the bushwhack. The bush, just way out in the middle of nowhere. It's really not that far from Baton Rouge. It's about an hour, but you can see there's not much around it. There's not much around this one. They don't want to have a lot of ambient vibration around it because they have no matter what you have, again, this thing's measuring distance of 1/10,000th of a proton. So it has to have extremely sensitive vibration control. So the less environment you have around there, the better. So how it works is this. The gravity wave signal, it's delayed in time between Livingston and Hanford. Light travels, the 3,000 kilometers in about 10 milliseconds. And that would be if the gravity wave started at this end and came like that. But the gravity wave could also come from this side too, and then they would show up at the same time. So they can, the waves appear shifted in time when they're measured between the two facilities. And you can kind of tell which part of the sky they're coming in because of that. And the measure delay depends on the direction of the wave. And then the noise, and the reason you want two is because you really want to have the noise. You want to make sure that you're seeing a gravity wave and you're not just seeing noise that's caused by some ambient situation that's around, like somebody's plowing their field or a truck drives by. Because again, these waves are 30 hertz to 7 kilohertz. They're kind of in the world we exist in. I mean, I'm speaking right now probably at about 500 to 1,000 hertz, somewhere in there, you know. It's crazy. So the displacement measured by interferometers, it's time delayed, and then you can try to help locate where it happens in the sky. And the accuracy varies. So for these different measurements. And with the two sites, I don't have any accuracy plots, but they're pretty, a lot of times they're narrow in the sky, but they might cover a good portion of the globe. So I'll know that there's somewhere like in there with a small line. There's some great data up on the site if you want to see how accurate you can find them. So I'll just show you a quick, this will work. Oh yeah. So what this is an example of two neutron stars colliding. So those are the two neutron stars, and then these the blue things are the gravity waves.
It's supposed to be animated.
They're called.
There it happens really fast.
Oh.
You get the idea.
You get the idea.
Try the enter key, enter,
Enter.
on the keyboard.
There you go. So they're kind of cool, and they go around like this. They're not going that slow.
Wow, faster.
And then they keep going faster and faster. And what's happening, the reason the two objects move closer together is the gravity wave is actually taking energy away. So that's why they just don't stay the same distance. So they go faster and faster, and then eventually they hit each other. And all these different frequencies are things that happen when they hit it, and then it just turns into this nice little bigger neutron star. So here, this was the first detection of gravitational waves, and that's a quote from the paper. It points to coalescence of two black holes, and the total mass of the two black holes was about 70 solar masses, and this orbital frequency is 75 hertz. So that means these black holes are rotating around each other 75,000 times a second, and they're like 75 solar masses.
Is it K or 75?
What?
On here it says 75 hertz.
75 hertz.
Did you mean K?
No, just 75.
75 hertz.
All right.
That's how fast they're rotating around, but they're about 70 solar masses. I mean, the total mass is too. So what they do is they have this, this is the measurement that they got from Hanford, and this is the Livingston and the Hanford on top of each other. And they have, they figure out what happened, a lot like how you do traffic sign recognition, exactly. They call it machine learning, which is the same thing. So they have all these simulations of different events that they then take the data and they match it to it. Just like you would if you're looking at a traffic sign and you got a camera and you don't know if it's a stop sign or 70 mile per hour. It's the same kind of thing, same kind of approach in the end. So all the measured signals are compared to this huge database of events to determine the most likely cause. And this is just a little different way to look at the same thing. So this is, they call it in spiral, where they're rotating around and they're rotating a little faster, you can see that. Then they merge, and then they call it ring down. Ring down is kind of like you got this big thing, you dropped it on a trampoline, it just kind of rings down and stops moving. So this was the first one. It was pretty exciting because this was, because this comes out of Einstein's theory of relativity, and it was from almost 100 years ago. So these are all the different LIGO discoveries that they've had. And how to read this map is the yellow down here are electromagnetic measurements of neutron stars. I actually don't know a lot about that. These are electromagnetic measurements from black holes. So that's probably material that's getting tore off from stars and moving in. And then these are the different gravitational collisions that they saw where they get two black holes and it goes into a bigger black hole. And here was two neutron stars going into a bigger neutron star down here. Neutron stars are typically under about 3 solar masses. A black hole obviously can be above that. This is LIGO Virgo. There's another facility that's called Virgo that is it's by Pisa in Italy. And so you can, but it doesn't have the same resolution as the 2 LIGO in the US. So, but when you put all 3 together, you can get a little better idea of where they are in the sky. So, this was just the LIGO Museum at the entrance. If you go there in the museum, you can get to see the Nobel Prize, which is kind of cool, the Nobel Prize medal. And it's a great museum. It's one of the best physics museums that I've ever been to and that my wife's ever been to. It really does concentrate on waves because they're trying to teach you about how waves work. But every single display works and it really teaches you something about waves. Like my wife's not mathematics at all, but you can see waves when you put sand on plates and they shake. And you know, parts are moving and parts are not moving. It's really an amazing facility that they have there for that. This is, when you go around, they'll take you around the whole thing. They'll take you inside, outside, they'll take you to the control room. Operations rooms, this is what they look like. A bunch of guys not doing much and just looking at screens waiting for something to happen, you know. So we were there too. So if you ever want to go there, they have Science Saturdays on the 3rd Saturday of every month, which we don't live close, so it doesn't work very well. But if you're there, it's not a bad thing, you know. But for a different time, this is what we did. Contact this woman, Kathy Holt, and try to get it attached to a school. And that's what they did. The site is right near Baton Rouge. The great part about us, when we were there, the school did not show up. So we got a private tour of the whole facility. It was really a nice little afternoon. This guy, William Katzen, took us on the tour. And so if you want any references, if you want to learn about it at all, there's all kinds of places you could look. This is LIGO Livingston. These are just, if you search with these words, LIGO Livingston, it will show you all type of data. Or LIGO Prescott Caltech. That's a real good one. It teaches about the Nobel Prize. Rainer Weiss, this is his original paper. He was one of the Nobel Prize winners. And then Amber Stuber, she wrote a book on gravitational waves that's actually, you need some, there are parts that are readable and parts that you really need a lot of general relativity to understand. But it's, but a lot of it's actually pretty readable. So, so that's it. It's a great place to go. If you ever get a chance, I highly recommend it.
Any questions? You covered everything.
I covered it.
Now,
How much did you get to see? Like, did you get to see like the control center?
When we went there, I mean, you walk around the whole thing because all the tubes are all they're all sealed, and you can't see any of the mirrors or anything. But inside the museum and the physics demonstrations, they have there's LIGO, and then they call it, like I said, LIGO A. So they have the old mirrors there, and they have mock-ups of the control system. And they have everything there. You can just, so you really can spend some time around it and see how all the mechanisms work. Awesome. And they're really descriptive. It was a nice afternoon. We were probably there, what, about 3 hours? Yeah. I mean, it was amazing. Yes?
How large of a staff do they have there?
Well,
Approximately, maybe.
yeah,
If it's a dozen or so?
Yeah, I mean, maybe under 50, maybe under 30 total. I mean, they have 3 or 4 operators that are working there, but I'm sure they have a lot of maintenance guys dealing with all of the equipment, you know. Like, just to go to vacuum, it takes 40 days to go to vacuum. So when you're installing everything, and they have all these different techniques. I mean, they pump it out, and then they use these electromagnetic techniques and heating to get a lot of the other atoms out. So I'm sure they have a lot of guys that are there kind of moving in and out, and scientists and that also. Yeah, but it's not like a huge. When you drive in, there's a parking lot, and there's what, about 20 or 30 cars, maybe. You know, that's it.
did you have to do this for one of your classes?
No,
No?
not at all.
I always double up when I have to do a presentation. I'm like, okay, can I make this for WAS and this?
I didn't want to embarrass you. Anyways.
All right.
All right, thank you.